In a previous video, we were presented with finding ways of arranging distinct objects. So in this example, if we wanted to know all the ways to arrange these distinct, and we have 5 distinct letters here, objects, we knew that would be 5 factorial. The question that we want to ask now is, what happens if our objects are not unique? So maybe we have the following set of letters. So if I want to find all the arrangements of these and the different words or strings that it spells, we can't do exactly what we did before. We know it's not 5 factorial because that would be treating these double E's as if they were one and they would move together. So wherever one of the E's moved, so went the other. So we know it's not 5 factorial. We know that it's also not 6 factorial because that's what would be the number of ways to arrange 6 distinct objects. So we know it's not 6 factorial. So let's see, let's see if we did do 6 factorial. We know that that's overcounting our arrangements because we have this double letter. And let's see exactly how it's overcounting. So, for example, if this was our arrangement, and I'm going to, even though these letters aren't indistinguishable, the E's, let's pretend like we ourselves can see that they're which one's which. So 6 factorial would count this as well as, this as a separate word. So if it would be treating those E's as if they were distinct. And so although we've coded them, these are in fact the same word. So we overcounted this one. And in fact, we can probably easily see, let's say that this was our word. If that's what we want to count that once, but 6 factorial would also count this word twice. And in fact, wherever I move those 2 E's, 6 factorial is overcounting them by a factor of 2. So we can easily fix this by dividing out 2. And to be clear, it's not just 2, although it is 2. It's all the arrangements of those 2 items. So it'd be better if we wrote it as 2 factorial. All right, let's see what happens if we have 3 of those. So let's say we have 3 E's. We want to look at all the arrangements of these letters, not all of which are distinct. So we have 7 letters here. We know it's not 7 factorial because our objects are not all distinct. And we realize that there's an overcount by all the arrangements of those E's. So let's say this is one of our words. And if I color-coded them this way, it's going to count this word as many times as I can move these 3 E's around, which is all the permutations of the E's. So we divide out 3 factorial. All right, let's do one more together. Let's say we had TEEXAAS. So now we have 2 sets of objects that are repeating. We have, let's see, 7 letters here. Right, over 1, 2, 3, 4, 5, 6, 7. Yeah, 1, 2, 3, 4, 5, 6, 7. We have 7 letters again. And, but we have 2 of which that are repeating. So if we start with 7 factorial, which we know is an overcount, it's overcounting all those flippity flops of the E's and all the flippity flops of the A's. All right, so if I were to leave you with one problem for you to answer, how many ways can we arrange, oops, I didn't spell that right, MISSIS, SIPPI. How many ways can we arrange those? Well, we see we have 4 S's, 4 I's, and 2 P's, and 11 total letters. So 11 factorial, divide out the overcount of the S's. the I's, and the P's. Yay.